very pleased to be here and able to give this presentation today. My talk is entitled Change Detection, Estimation, Segmentation. The most common form of this problem is a process where the level changes from time to time, and that is included as a special case. But there are other features as well that can lead to changes. And the one that I'm going to use for all my examples today involves change in the slope of a process, so that we end up with a broken line type of regression problem. Unique features are that we will use the maximum score statistic in some sense or other, and we'll be interested in segmenting when there are multiple changes, and we allow a first-order autoregressive dependence to minimize false positives when there is dependence. This poses some problems because when there are true changes in the level or slope, estimators of the autoregressive parameter and variance can be badly biased, and this can lead to a loss of power that we have to discuss at the end of the talk. Modifications of the natural estimators to deal with this difficulty are partly successful, so I'll explain. And then the main feature, I think, is that many different examples, temperature time series, atmospheric CO2 levels, the incidence of COVID-19, excess deaths, copy number variations. And I should point out, this is joint research with my colleague Xiaopeng of the Chinese University of Hong Kong. So this is the general model, which I've written in a continuous time formulation, which can be convenient, not necessary. We have a process which consists of a drift, typically either a constant or linear, but then superimposed on that are possible signals of the form of a function f of s minus tj, where tj denotes the position of the signal and xij denotes its amplitude. And for the moment, we should just focus on the case where there's only one value, tj, t1, say. Then there's an autocorrelation and white noise. And there are examples given here. The indicator that u is greater than 0 indicates a traditional change point problem. The positive part function indicates a change in slope, assuming, say, mu s is itself linear, then positive part function indicates the change by the amount xc. Then can be the indicator of an interval, that is a change in the classical change point sense, but a transient change, and so forth. The parameters of primary interest are the location t of a change and the amplitude, although we'll focus more on the location than the amplitude. And the signals are the nuisance parameters, denoted generically by theta, are the constant drift or the linear drift, and the parameter rho, the autocorrelation. I'm assuming sigma is known. We have to come back to that because I'm clearly using examples where I have to estimate it. The first thing I'd like to talk about is setting a standard for detection of a threshold of a signal. And again, let's focus on the case where there's only a single signal. By standard likelihood theory, the score statistic, which I should have showed you back here. I should have talked about that. So we're going to, given t, the efficient score for testing that the other parameter, xc equals 0, is the partial derivative with respect to xc the log likelihood evaluated 0 and theta hat. Theta hat, the maximum likelihood estimator, when under the assumption that C equals 0. And the feature of this problem is its statistical feature is its irregularity. T and Xc are confounded parameters. We're going to focus on using the score statistic to test the hypothesis Xc equals 0, which gives us a process that depends on T. And we will typically do something like maximize that process with respect to T. But for fixed T, standard likelihood theory tells us that the score statistic can be expressed in the form of the partial with respect to Xc minus Fisher information for Xc and theta, Fisher information for theta and theta inverse, and the partial with respect to theta. And those are all evaluated at known parameters in the asymptotic framework. So I'm going to rewrite equation 2 in the form of equation 3, which just emphasizes the structure we have. The point is that asymptotically, the first Fisher information, I Xc theta, which I've written psi prime of T, is a constant. A does not depend on unknown parameters, and L theta does not depend on T. We'll let sigma of S and T denote the covariance function of the process under the hypothesis Xc equals 0, and we will standardize the process and call that Z sub T, dividing by its asymptotic standard deviation. And this representation allows us to approximate the probability that the maximum ZT is greater than or equal to B, which with the subscript 0 denotes that Xc equals 0. That is that the null hypothesis of no signal is correct. And then this represents type 1 error. And by approximating this, we can control the type 1 error. The approximation depends on the form of the specific statistic. For the broken line model, the process is sufficiently smooth that we can use essentially Rice's formula. And I've written here with equation 5, the approximation. And a simple numerical example, we consider the annual average temperature of the Netherlands from 1901 to 2016. These are available for virtually every country in the world. And so T is 116. The threshold in the case of the Netherlands, the maximum value of ZT, the observed maximum, turned out to be 4.01. And then the approximation gives the value 9/10,000, so about 1 in 1,000. So it's just a simple example that we can do this calculation. So we have an idea what the type 1 error is if we test for a single change, or at most one change. There's a plot of the statistic itself. It's a plot of the square of the statistic, which will be convenient at some point for talking about confidence regions, but it's maximized at about 1979. And this is typical. If you plot annual average temperatures for most countries in the world, the local maximum will be about between 1970 and 1985, and will typically be statistically significant according to our test, but often is not, because the noise level can be quite substantial. Now, here I consider a multidimensional example, which has been raised as an interesting statistic to compute at the time of the COVID epidemic. We consider the first 15 weeks of 2020, for which data are available from several European countries, as well as from the United States, and consider Germany, France, and Spain as three countries. We assume independence between weeks. So here I'm, and for each country separately, I'm also assuming independence. So I'm setting rho equal to 0. And each country seems to have a slope increase in the excess deaths. That is the total number of deaths minus the expected number of deaths based on the recent history of recent years. The numbers are small and the results somewhat unclear. Spain is not significant at the 0.05 level. France is, but not at the 0.01 level. And the p-value for Germany is 2 in 1,000. We assume independence between countries and consider the norm of the three-dimensional process of the kind that we had just a moment ago. And the p-value for indicating a slope change after 8 weeks is 1 in 10,000. So by combining the information from these countries, we make it much clearer that at least in total, there is a slope change, and we would have to look more carefully to make sure that we haven't just dragged Spain along by let Germany drag Spain along and make it appear that it also has excess deaths. But I think it's possible to do that, but I will not try to do that here. Now, I want to talk about segmentation because the primary interest is going to be in the case where there may be more than one signal. And now I'm going to write my statistic that I've written before as Z of small t as Z of small t and capital T, where capital T represents the length of the time interval of observation. And now there are two methods I would like to consider for segmentation, at least initially. One I call a pseudo-sequential method, where I act as if I'm just observing the process from 0 to time capital T as capital T increases. And I consider the first time, or perhaps a subsequent time, but let's say the first time that this statistic, the first time capital T, that the maximum value of this statistic over little t exceeds some threshold B, and that can be used to detect the first change point. Then that process can be iterated starting from the detected value of little t to detect perhaps a second change point and so forth. Of course, that requires a different significance level threshold. And if I denote Q as written here, I can find an approximation for Q. It's rather more complicated, so I won't try to explain it in detail. But to say that a feature of it is that whereas the single index approximation involving only small t was a direct application of Rice's formula, here we have to take into account a rather more complicated structure, because when capital T varies, the process is not a smooth process. So we can use this approximation for the pseudo-sequential segmentation, as I explained, or it could actually be used in a sequential way, because when we estimate the slope, we only do it with regard to the data observed so far. And we can obtain a similar result if we consider an interval capital T0 to capital T1, and we can maximize that over all possible T0, T1, and that suggests we can actually search over all possible intervals to find a change point within the interval. Search over all possible T0, T1, looking for a change point little t between the two. Or we can use, as suggested by Frislovics, a random selection of background intervals, which allows us to do more or less the same thing with considerably less computational effort. Here we'll consider as first example the northern hemisphere temperature anomalies from 1850 to 2019. These are as computed by the Berkeley Earth website using some data from the East Anglia group and using their other data that they have collected. And the reason this is interesting is that if we look at a plot of the data, which I'll show you in a moment, it suggests there might be multiple changes, and that's what we're interested in now. For the example, here we have 170 years. If we set B equal to 3.77, and it's just so we have at least a minimum number of 5 observations before we start trying to detect a change. And set rho equal to 0.3 to sort of protect ourselves against too much autocorrelation. We'll see that that's a reasonable result. The pseudo-sequential method that I just described detects slope changes at the 64th, 94th, and 126th year. At the conventional level of 0.05, the method using all possible backgrounds detects essentially the same 3 change points. And now, when we've done the multiple change point detection, I find it's very helpful to run a multiple regression model, just a simple model, with the assumed 3 changes assumed to be true, which makes then the nonlinear regression model into a linear model. If we do that with the current data, we get an R-square of 0.92 and find that rho is actually 0.33, or at least it's estimated to be that. And here is a picture of the results. We see that the temperature anomalies in 1850 start off moving rather flatly. Around 1912, they slope upwards. Then they actually slope slightly downwards, but more or less flat again. And then the temperature really takes off in about 1970, which is, as I say, what you will find if you look at the individual countries of the world, you'll find that there's a very steep slope increase in the late 20th century. And that here is consistent with the northern hemisphere anomalies for both the land and ocean. I might add that if we did land by itself, it would not be quite so clear that these multiple changes. The multiple changes is driven by the ocean, which quite clearly has these multiple changes, or at least I would say, based on my experience looking at these data quite clearly. Now, there's the 2 methods I've described so far for segmentation are what I would call bottom-up methods, because they try to find local changes by looking at the local background. So you see a change that has occurred relative to the background, but it's a background that's relevant to detecting a particular change. It's also possible to do a top-down procedure, and one that we found very useful is one that attempts to detect slope changes in pairs. So we consider the statistic, which is the statistic we had before. The numerator that we had before was called V sub t. Now we make a pair of V sub s, V sub t, standardize, and make a chi-square type statistic out of that by standardizing it by its estimated standard inverse covariance matrix. H is a parameter that represents the distance between changes. It can be fairly small, but probably shouldn't be 1, because you pay very heavily if you try to detect changes very close together. And we can compute an approximate threshold. And again, this is now a sort of a generalized Rice's formula. Now, this search can be iterated. And if we assume in early iterations only true positives are detected, that is, say, at the first step we detect 2 changes, and now we try to find a third one, so we've got changes at S and T. By iterating the process, I mean we consider the interval from 0 to S, S to T, and T to capital T. the iterative process does not create multiple comparisons issue if the changes detected up to now are correct, because the probability is roughly linear in the length of the segment search. So the probability after a half dozen searches, if there should be so many, is just the expected number of false positive is just the same as what we started with in the beginning, assuming that the first however many searches have yielded positive results, have yielded more or less correct positive results. And if we return to the Berkeley land-ocean data to detect the change in pairs, we get essentially the same results. There are a few examples for which this seems to be a tailor-made method. And those are examples where there are just exactly two changes. For example, the Berkeley Earth website gives annual average temperature anomalies for individual European countries, beginning in the year 1753. The East Anglia website begins its temperature record in 1850, and the National Oceanography, Aeronautics and Atmospheric Administration of the United States begins their record in 1880. The Berkeley Earth website is interesting because it leads to the possibility that we actually might see a change that occurs before the other records even begin. And these data are pretty noisy at the beginning, so we can't be too enthusiastic about what we see, but it does seem very interesting. Now, for these individual European countries, and I'll show you a plot in a moment, the pseudo-sequential method and all possible backgrounds method often detect one slope increase in either the late 19th or the late 20th century, but they typically don't detect both. But the method to detect paired changes often detects two changes. And here's just a simple example. The annual anomalies of Switzerland, where positive slope changes can be detected in the 135th and the 228th year by the method for detecting changes in pairs. And the other methods detect only the first of these, although the pseudo-sequential method, and this points out a disadvantage of it as well, it detects both methods if it is run backwards through the data. It's not invariant with respect to the ordering of the data, which would be preferable for the problem that's been formulated. So one could consider running it forwards and backwards at a reduced significance level for each run, but I haven't really studied that issue. This is just a simple example. We're running it backwards at the same 0.05 significance level produces two estimated changes. And there's what the Swiss anomalies look like. And this is typical of the European countries with these data. That is, from 1753, the temperature seems to be decreasing quite substantially. Around 1880, it begins to increase. And then again, in the late 20th century, around 1980, it takes off rather sharply. So this sharp increase around 1980 is a very common feature of these temperature data. How exactly we interpret the initial decrease is not so easy to say. This could be a feature of the so-called Little Ice Age. There were very powerful volcanoes in the early 19th century that had the effect of cooling the Earth rather dramatically for a short period of time. So I think these data are actually quite interesting, but much more might be said about them. Probably not by me, because I don't understand the scientific features that might appropriately go into a more detailed analysis. So our broken line model can also be used for tracking the incidence of the COVID-19 epidemic. For example, in Italy, for the first 124 days after the first case appeared on 31st of January, the pseudo-sequential method puts the first slope increase at 20 days, a large slope decrease at 63, and another much smaller increase at 101 days. The method, using all possible backgrounds, misses the first change, although the slope at time 0 sort of compensates for that. And the best result of the 3 methods comes from the method designed to detect 2 changes at a time, which first detects changes at 36 and 58 days, and then detects a single change at 101 days. It's interesting to note here that the pseudo-sequential method could also be used as a legitimate sequential method. And if it were applied to the COVID data from China, which reported its first case on the 31st of December in 2019, and if we calibrated it to allow 1 expected false positive in 100 years and set rho equal to 0.4, it would in fact detect a change after the 27th day, that is still within January, and it would estimate that change to have occurred on the 22nd day. I might add that the reporting of data from China in the early days of the epidemic was very irregular, but this is what we get by taking the data on faith. There's a plot of the data and my best fitting straight line from Italy. And actually, so we see that the data starts off more or less flat, then it has a sharp increase for a period of time, a sharp decrease, and sort of tends to level off as it gets back near 0. And this is also a fairly typical pattern, although some countries have not yet reached the leveling off phase. And the extreme outliers at about right here are also typical of these data, which suggests that there was a reporting failure where 0 cases were reported on one day, and then compensation appeared the next day when a huge number of cases were reported. And this is true of most of the countries of the world, that they've had these what I interpret to be reporting failures. Now let me spend just a couple of minutes talking about confidence regions, because this is, I think, sort of a novel feature of our work and can be very useful. If we use either the Kac-Slepian model process or equivalently an application of Lecombe's large sample theory, we can find that if we assume there is a change point at the point t, and we look in a neighborhood of t at the squared value z sub u, so we look at a maximum of z sub u squared minus z sub t squared, conditional or not on z sub t, we find that this is approximately the first derivative of z squared, first derivative evaluated to t, divided by the expected value of the first derivative squared, which, since we're talking about an approximately Gaussian process, will be approximately chi-squared. And hence, 0.9, for example, or 0.95, confidence region for t is simply the set of all t that has z sub t squared greater than or equal to maximum over u, z sub u squared, minus an appropriate chi-square percentile. And this is exactly what would occur in a regular problem from regular likelihood theory if we use a likelihood ratio statistic with 1 degree of freedom. And we can use this result otherwise to give what I call an approximation for the local power. Here, power should not be interpreted as just the probability of a true rejection, but it should be a probability of a true rejection that gives an indication of the true value of where the change point occurs, which here I've written as tau rather than t. And that's what I refer to as a local power without being more precise. Now, a particularly challenging example is the Central England temperature since 1760. This time series actually begins in 1659, and it's pretty noisy at the beginning, which I'll show you. So to make it more or less comparable to the Berkeley website series beginning in 1753, I began this one. I chopped off the first 100 observations, began this one in 1760. And a change is detected about 1980. But the plot that we'll see in a moment suggests that maybe there was actually an increase about 100 years earlier, as we saw with the Swiss temperature data. But here it's not so clear that there is such a change. However, a 95% confidence region extends 10 years to the right of 1980, but almost 100 years to the left. I think it's maybe 97 years to the left. So it includes the region that appears it might have had an earlier change. Here is a plot of the statistic for detecting at most one change. And you see here is the actual maximizing value, but the data are very noisy at the beginning, perhaps reflecting, again, something having to do with the so-called little ice age. And here at 200 in this picture, which goes back to 1659, the slope has begun to increase. So that's about 1880. Then it increases further in the 20th century, and that's the point that's picked out by our statistic. However, since the confidence region is based on the distance the statistic has fallen below its maximum, we get a very long confidence interval to the left, which seems appropriate for this problem. So even if we don't detect this as a separate change, it's hard to localize the maximum here and say that's where the change occurs. Now, I want to say something about estimation of rho and sigma squared. There are a few cases where it's fairly easy and other cases where it's much more complicated because they can be badly biased under the alternative hypothesis that there are actually genuine change points. And if we use values that are too large, it leads to a serious loss of power. And so I've tried different things, none of them entirely satisfactory, but after a while you get enough experience to sort of think you know what you're doing and probably are making a mistake that way. First of all, I've assumed stationarity in rho and sigma squared. So if there's a known segment of the data without local signals, and there are some examples, we can estimate these parameters from that part of the data. If we assume observations are independent for problems, say, involving just a level change where there's no slope, we can use the sum of squares of pairwise differences, which is now suitably normalized and an unbiased estimator of sigma square. But this only works if the observations are independent. And if there is a slope, we can use second order differences to accomplish the same sort of bias removal. But then we are, in effect, reducing our effective sample size somewhat. Many of our examples involve time series where serial correlation must be regarded as a possibility, and I do not have a preferred method for doing that. I would say that in all examples that I've discussed, I've either estimated or chosen what I think is a reasonable value of rho, and then with that value, I've estimated sigma square by the usual sample variance. But this is still a problem that causes some difficulty each time. And of course, the fact that sigma square is rarely homoscedastic and rho itself can vary poses additional problems. But I don't think it's, based on doing a large number of simulations, I don't think the problems are severe. Somebody else should examine the data and criticize my analysis. And now let me terminate by just giving some of the references that have motivated our research. Xiaofang and Jian Li and I have a paper that's about to appear in the Annals of Statistics, where we do the standard change point model, assuming independence and only our changes in level of basically only a Gaussian process, although it can be generalized to exponential families. And the current research is reported on an arXiv reprint. And now I've listed 3 other papers that provided quite a bit of motivation for our problem formulation and work. In particular, let me repeat the Frisovic's wild binary segmentation, where he suggests we only consider a random sample of background intervals in order to speed up the process compared to using all possible background intervals. It is something we've done, and it seems to work very well. Of course, we have computed a threshold that allows us to pay for all possible background intervals, so we can always fall back on that if we think that the wild binary segmentation process has not been adequate. With that, I would like to close and thank you. Thank the conference organizers for the invitation to speak, and for you, the audience, for listening. Thank you.